So thank you very much. I hope you can hear me quite well. Let me know if there is any kind of issue. As I said, it's just this part of the board that is already written. Then I intended to keep writing. I thank you very much the opportunity to be speaking. I'm really, really sorry to give in this Zoom talk. I know that this can be like very frustrating in many sense, but there was no other way for this period of time to myself. So this talk is like based on joint work, hopefully finished manuscript with Lino Grama, Ludmil Katzarkov, and Maxim Kontsevich. And it's like it was brought to life by the attempt to try to connect G equivariant birational geometry with this atoms story that's quite recent. And throughout this talk, I'll like do my best to try to explain also the atom formalism itself, and I'll try to make my case that this is a formalism, and it's like, of course, driven with my perspective, with many formal details, and G equivalent birational geometry. I must say I'm no expert in any of these two fields, so I'll try my best. Throughout this talk, we'll follow some conventions, like we'll consider X to this n mod, over C as like smooth projective n-dimensional algebraic varieties. Usually we shall pick n being equal to 2 or 3. And often we shall consider like some finite groups of the group of automorphism of these varieties. And where the action is always on the variety itself shall be assumed to be generically free. Often G shall be the p-cyclic group for P prime. We also let the convention of X to G being the fixed point set decomposition. So as some kind of prelude, I'll start already by stating some theorem. So let's say theorem A. I'll adopt also like this short notation by C. It stands to Cavenaghi, that's myself, Lino Grama, Katzarkov, and Kontsevich. This is the following. We pick them two-dimensional varieties, and we look to Z2, generically free actions on X. All right, and then we collect this Z value stuff here. We take the Euler characteristic of the fixed point set, and then we take some sum of the degree of the normal bundle of certain P1s inside of X, where I'm going to explain here. So let me just draw this. Oh, that's color is going to be terrible. So let me just call this by Zager. And then what we'll have is that this sum here, where that runs, the summation runs over all of the P1s appearing as irreducible component in the fixed point set. This is this quantity here. I'll say like 1. Then 1 is a Z2 birational invariant. What do I mean by this being a Z2 birational invariant? It means that every time that you try to perform blow-ups along here, like a finite collections of points that are invariant under Z2 actions, then this quantity remains invariant. All right, so it's like usually this. And yeah, of course.
So what's the first summon?
Yeah, sorry, is the Euler characteristic of the fixed point set.
Oh.
So here, it's topological quantity. Let's put like Euler characteristic. It's like topological, not holomorphic Euler characteristic or anything like this. It's really topological. So then the theorem B, from which theorem C is indeed, as can see as some kind of corollary, is the following. We still consider surfaces. So here. But now we take ZP actions on X, and then I claim that the quantity that shall be, again, the Euler characteristic of the fixed point set minus this super trace that I'll explain in a moment of age, sorry, not age, A. So here, A, then you pick the cohomology ring of X with coefficients in C. This I'll call 2 is a ZP birational invariant. Where, as I told you, so since we do have like a group action on the smooth projective variety, we do have actions on homologies. I pick A to be a generator of the ZP, and then I look to the induced map here in this homology. I treat the homology as like a super vector space, and then I take the trace. So we have then, we can think it as A as map on H star to itself, like some endomorphism, and take super trace, take super trace. But not only this, so you see that here that we have a P action is still in surfaces, but if, and this only holds for P equal to 2, that's the following. If P equals to 2, then we have a 30 birational invariant that shall be precisely the super trace, the same from equation 2, plus the sum of the degrees of the normal bundles of the P1s appearing as fixed point set components. So here we put 3. We have then that this sum is the same as Jagger as before. So let's take a more careful look to all of this. Theorem A, sorry, is for Z2 actions on surfaces. I claim that this is a birational invariant, Z-valued birational invariant, and it's obtained by taking the Euler characteristic of the fixed point set plus the summation of the degrees of the normal bundles of P1 sitting as irreducible components in the fixed point set. For any P prime, we can like do a bit better and include this Euler characteristic, but now we should take the super trace for the action of any generator in homology. And in particular, when P equals 1, we also have a Z-valued invariant relating the super trace, but now with this degrees of normal bundles of P1 sitting inside of X as irreducible fixed point components. So these are like some invariants in dimension 2. Let's quickly see how they work in 2 examples. So the first example is this Clebsch surface. What we shall take is our smooth projective variety shall be x1 square, x1 cube plus x2 cube plus x3 cube plus x4 cube. Whoops. I hope I don't do this quite often. Yeah, sorry. So this is x3, of course. This is going to be x4 to the cube, then equal to x1 plus x2 plus x3 plus x4. We raise this to the power cube. We look these coordinates x1, x2, x3, and x4 sitting inside of P3. Okay. And then we shall consider a Z2 action. Let's write this as sigma E, such that sigma square. We consider this action on P3 first, that shall only make this exchange here. We exchange x2 with x1, and then we exchange x4 with x3. This action restricts to an action of Z2 on X, so it induces a Z2 action on X, and is a computation that the fixed point set for the Z2 action are precisely 3 points. Being these 3 points, the invariant in theorem A, that is the one with the Euler characteristic and the degrees of the normal bond of P1s, is precisely the Euler characteristic of xz2. We don't have P1s in this summand, so it's only this. That shall be precisely +3. So this is an example where we can collect this as the valid invariant. Then very, very quickly again, another example. This, I think I will omit one. So I picked this that I suppose Ludmil more or less commented yesterday. We take then the that's going to be the blow up of P2 at 3 generic points, three general points. Okay. And we can see this guy here sitting on P1 to the power cube, right? And we can introduce now a Z3 action on here, even in this way. So each P1 contributes as some homogeneous coordinates, right? So I cyclically permute these P1 factors. Then I consider the restriction of this action on this x1, 1, 1, 1. So then as restriction of cyclically permuting the P1s. The P1s here on this P1 to the cube. Then you can compute, for instance, that x1, 1, 1 with this Z3 action is again 3 points. So the Euler characteristic of this guy shall be 3. And once you choose a generator A to Z3, it's like a more intricate but not hard computation, but I must admit that I struggled at the beginning to compute it, the super trace or the cohomology of this guy. This is precisely 1. Thus, the invariant in theorem B, so let's put this, the Z-valid invariant. Sorry, generically my writing is bad. Today is the worst. The Z-invariant is 3 minus 1, that shall be 2. Okay, so this is how these invariants work. It's like pretty simple. You must give me some examples, and then you compute the actions explicitly. You collect the fixed point set data, and maybe you have to compute some super trace when P is not equal to 2, but you can capture this ZP invariants. And the nice stuff is that then you can ask questions about what are these invariants for like projective space with certain linear actions by these groups, and check whether they would be like ZP birational to this projective space or not. Okay, as people usually do. Any question, comment, criticism so far? So when you look to this kind of like z-valued invariants, you may ask yourself, so how should like you would get how you in life would think of formulas like this? And this is the tricky, and this is the same question that I asked Maxine like at least 4 times during the intercourse of like our discussions, is that like if you are giving such a formula like this, how would you know that they're like a invariant and they're equivariant blow up? And the answer is like we don't know how to guess these formulas, but with this atoms formalism combination with symbols, that so far there's no atoms, it's like purely um, classical content in some sense, in the sense that, not in the sense, but in the precise sense that these things here have a very concrete meaning, geometric even. And the main point is that like this atoms formalism, it will help you by the combinations with the symbols story that I want to say that it was initiated with Maxine, Tschinkel, and Pestum, at least on my understanding, provides you many ways to guess invariants and new ZP invariants. We only worked with ZP so far, but we could do better in many cases. So let's move on. This is only for surfaces. I'm gonna state here an analogous theorem in dimension 3, where now you're gonna see the first appearance of atoms, and then we shall definitely digress to explain a bit about atoms and the Hodge structures on atoms to come back to show how these symbols meets atoms or vice versa. So the theorem C that I want to state, I will not repeat the name of the people, that's like the same at the beginning, is the following. We pick now three-dimensional smooth projective varieties. We look to ZP actions. And now you give me some smooth projective curve with genus, say G greater or equal than 1. And the statement is again another formula that shall be a ZP birational invariant. That is the following. We look to the fixed point set. We look to this decomposition in irreducible components. And then you shall collect the z-valued invariant as you subtract the number of these components here in the fixed point set that are isomorphic to this curve C that you gave me on the beginning. Now you're gonna subtract twice the number of these components on the fixed point set that are birationally equivalent to P1 bundles over the curve. So, and now, so we subtract we look to the fixed point set decomposition, we collect it. So is there any component which is like isomorphic to this curve that I fixed at the beginning? If yes, then I count. Then I look to the surfaces components here. I look then I can like check. This is like the most tricky part. That's is there some that are like birational to P1 bundles over the same curve? And then I compute the numbers, take -2 twice. But now we were gonna add something here. And this is something is the trick atom story. And I'm gonna denote it as like the number of ZP atoms that shall be isomorphic to, and I'm like robbing you now. the way that I'm gonna write, perfect complexes of curves. So this is like a general statement. And now I will devote most part of the time of the talk explaining the meaning of these ZP atoms and what they mean to be isomorphic to perfect of C. And again, how can one guess a formula such as this? And this formula is guessed in the same way that we guess the formula on theorem A and B. And so this comes from this combination with these atoms with symbols. But it's very important in the model as natural to remark that if God gives you a formula such as this, you don't need to know any kind of like, at least to theorem C, atoms or like anything else to prove that this formula is a p-birational invariant. You know the possibilities of the possible blowups, right? And you show that this thing like stay invariant under these equivariant blowups, meaning blowups along the centers that are invariant under group action. So if God like gives you this formula, then you can prove it the way that is like someone very skilled in algebraic geometry would prove this. And in this paper that we are hopefully finished, we guess the formulas by these relations, and then we give like straightforward proofs, checking that they are invariant under equivariant blowup. So there's no trick on this. This is the straightforward proof. The main thing is like how would you guess such a stuff?
So sorry, what is the theorem? What's
Yeah,
statement?
sorry. Yeah, sorry. You have a three-dimensional smooth projective variety with a ZP action that's generically free. Now you fix a smooth projective curve with genus greater or equal than 1. You fix one. Okay, you choose one. Then you look to this fixed point set decomposition for the ZP action on X3, so the three-dimensional variety. Maybe I just should like erase this 3 here to make no confusion. So you look to the fixed point set decomposition, and you start to look at the components of this fixed point set decomposition. All right. Then you check, is there any component that's isomorphic to a curve C? If so, then you collect the amount of them. All right. And subtract this amount. Then you look to these components that are like surfaces that are birationally equivalent to C cross P1. You compute its amount and then multiply by twice, and then subtract 2. And then you look to these things, mysterious things that I didn't tell you already. What are these ZP atoms isomorphic to perfect complex of curves? And you add the amount of this. So this is going to be like, this is going to give you some Z-valued number. And this is a ZP birational invariant. Is a ZP birational invariant. Is it clear?
What's the role of the curve? The C is anything.
Yeah. You can choose it like accordingly. The role of the curve, it's because if you look to projective spaces, then you look to finite group actions, like linear finite group actions on projective space, at least on smaller dimensions. You cannot expect in the fixed point set like some higher genus curves, right? So this is chosen specifically to try to constrain the possible numerical values of these invariants.
What does it mean? It's a ZP birational invariant.
It means that is this quantity that's a z-valued quantity is invariant under Z equivariant blowups. Sorry, ZP equivariant blowups. It doesn't change under equivariant blowup.
So C is different distinction of
Yeah.
variation.
So I'm still confused about C.
For the, you fix C. C is fixed. Okay. So for a given C, it will be variation. Maybe zero.
Yeah,
You can input different C's.
Okay.
As far as I can understand.
yeah, this is it. You can
Okay.
choose it.
I see.
Sometimes you'll get zero, sometimes.
Okay.
Yeah.
Some C it works. Okay. I see.
Okay. Is it clearer?
Yes.
Thank you so much for people helping me clarifying this. And then like in the next moments, from now on, I'll try to explain to make sense of these ZP atoms, and then how you would use these atoms mid symbols to guess this kind of formula that I said once again. Now that we clarified that these things being ZP birational invariant means that these quantities, once fixed in the curve, for instance, on the student MC, are invariant under equivariant blow-up, how that you can prove this like without referring to any other kind of theory. It's just like studying the equivariant blobs possibles, the possible equivariant blobs. So I quickly recall on this theorem of this theory of atoms to make sense on what I'm saying. Again, I'm sure that Ludmil provided a perspective on this that is most likely different from mine because he's one of the inventors of this, and I am the one of the ones that are trying to understand it with my own background. So I'm not claiming that this is the way that you should think. This is the way that I think. Okay. This theorem of atoms is first and foremost, for me at least, a formalism. A formalism. And this means that it depends on some choices to study, and different choices give you different theory of atoms. So this choice are constrained by what is named like view cohomologies. I'll make precise sense. Don't worry. But the point is that I hope that you see when I get there that as this depends on choice of view cohomologies, you can treat different kind of problems. Equivalent birational geometry problems, or like Professor Chelsov was like explaining yesterday about these orbifunnels that are well formed. You can try to use like appropriate cohomologies for stacks and develop this theorem atoms for stacks to study that kind of problems as well. And it has its origins for like homological mirror symmetry, but it started to work apart. It is developed in, so this is HMS for homological mirror symmetry. It has like its origins from this, but it is being developed in a way that it doesn't rely on, but so it does not rely on, but you can. And what I mean by you can, it is for the best to do computations if you go to this Landau-Ginzburg model, like in many situations. And I hope I make this clear. So I'm really sorry, this like handwriting is like terrible. Let me know. So this is a formalism that depends on choice of cohomologies, view cohomologies. It has its origins on homological mirror symmetry, but it does not depend on homological mirror symmetry, but you can. Any comment, question? And unfortunately, so like, let's say, unfortunately, I'll have to make some comments. I'll have to make some comments. Assuming some knowledge, let's put like small knowledge on Grama-Witten theory. But this is not crucial to the understanding of many parts, but unfortunately the definitions are like deeply connected to Grama-Witten theory. I'll have to assume a bit on this, and I hope you may find the interest to fill the details soon enough. So we're gonna fix then X, again, our smooth projective variety. Here, there's no constraint about the dimensions, but for concreteness, you can think of that we are on this dimension 2 or 3. We look to this cohomology ring. All right. And we're gonna see this as like even graded, super vector spaces. So even, odd, sometimes even like it's for the best if we treat this cohomology as topological spaces and look at this decomposition as as like a, you look to this cohomology as a topological space. That's of course a vector space, but as topological space with the structure of C analytic supermanifold. We are gonna pick then some element here on H, and we write this as like the term that has degree 2, meaning it belongs to the second cohomology group, plus the terms that do not belong. This may includes like all the possible this includes definitely all the possible odd degree terms. And from Grama-Witten theory, we are very much tempted to define some kind of like function here that depends on this age. And I'm gonna write an expression here for the sake of completeness, but I'll add no detail regarding what's written here. But it's like you're gonna speak 3 factorial, then you're gonna look to this x to the power. This is like cube. Then you take the summation over beta different from 0, where this beta here is at least I can tell you that they belong to the second homology of x with coefficients in z. I take the exponential. This is exponential function. So I integrate this part, and then I multiply by the summation. So this is n equals to 0, 1 over n factorial, and then integrate on these classes that I will say nothing about. Then the part different from 2. So what I'm doing here is like we agreed on taking this smooth projective variety. We look to its homology ring with coefficients in the complex numbers. We decompose an even or odd part. Now we pick an element on this ring. We look to the part that has like a degree 2 and the remaining. And we want very much to define a function like this that like, so defined on this age. So it's a function on this ring, and it should behave like this, meaning it's given by some strange integrations that depend on this second homology classes and this exterior powers here, and this strange class. That's all from Grama-Witten theory. But the main point is that we cannot always define this. So warning, there are some issues. There are issues. And the issues is that this not necessarily gives an analytic function on this cohomology when you see this as like C analytic supermanifold. There are issues regarding this F0 not being analytic, for instance. But what we shall do here for this talk is to assume that indeed we can find some like open set on this homology where this function makes sense and is like analytic and everything else. It's very important to say the following. For concrete smooth projective varieties, in all of the known examples where you can try to define this kind of potential function here, you can always find this neighborhood with this property. There is indeed, there is the conjecture that this is always possible for every smooth projective variety. It's not completely proven, but for all the concrete example, this exists. The atoms formalism, like done right, using this kind of F bundles, it avoids this thing by passing to a non-Archimedean field, but we shall not go there. But the main important thing here is that, the most important thing here is that we assume that there's some kind of like analytic function defined on this open set non-empty on H, where on H, because with this, so assume we have this guy where F0 is defined in an analytic. With this, we can indeed make a very important definition, that is this of the quantum multiplication. So let me hurry. We have this quantum multiplication. Quantum multiplication. And the quantum multiplication is obtained from these potentials. When you put coordinates, what you have is the following. You pick this guy belonging to here. Then the quantum multiplication that I'll denote by this star with gamma here, meaning it really depends on the choice of this gamma. And this is gonna be multiplication on the tangent space at gamma of this open set. And because this is open, this is the tangent space of the cohomology, but also the cohomology itself. So it defines a multiplication on the cohomology and makes the cohomology with this then family of products indexed by these elements, make this commutative associative superalgebras. So commutative associative unital superalgebras. Let me write like this, superalgebras. Because for some reason, so we have defined this open guy that we assume that's like so non-empty, sorry. Non-empty, where this function is like well-defined and analytic. Then I claim that for each element on this open, you can define a smooth multiplication indexed by this gamma on the tangent space of this open set, that because it's open is the tangent space of the cohomology, because it's a vector space, it's the cohomology itself. And what is the relation with this guy? This multiplication with this potential function is that it's given by the third derivatives of f in gamma. So you can see then this as a map from T gamma ux to the power cube to C. Or also you can see this, because it's open, as a map from age to C, or by using Poincaré pairing, map from this to this. All right. And like associated with this, we have an Euler vector field. That's going to be a distinguished vector field. So it shall be a guy that belongs to sections then of this open set. So the domain is this, and we look at its tangent bundle. We have the sections. I'll not write its expression to save some time, but there is this vector field. And so you see that we have a bundle, that's the tangent bundle over this open set. Then the quantum multiplication gives to each point a structure of unital commutative associative algebra on the tangent fiber that we identify with the cohomology. And the Euler vector field as a section of this bundle also gives us some a vector on each T gamma. And we can consider then this operator. There is operator. There is an operator. Operator. That's going to take gamma. Then we just put this. And this guy is an operator from the tangent of gamma ux onto itself. All right. Being this guy, this endomorphism, such that this is nothing but the tangent space of age. That is age. We can try to do the following. We pick I'm running out of time, so we pick gamma here. We pick gamma belonging to this guy sitting on this. So we only take gammas that are composed by even degrees. And in this case, our operator is our operator shall be an even operator. So we shall have this even operator here. That's gonna be an operator here. An endomorphism from here to here. And we can collect, for instance, its spectrum of this operator. This is some collection of eigenvalues. And the main trick on this atom theory is that to each lambda, we can associate some Hodge structures. So how you do this? So we take this even part And from the point of view of homology, this sits on this H2 star XC, right? By like, because the X is smooth projective, then you have the composition, so you have Hodge structures here. And the point is that I'll have to skip many stuff here. Very sorry for this. So the point is that if you take, for instance, the category of pure Q polarized pure Hodge structures, you take the category whose objects are this Q polarized union of Q polarized Hodge structures, and the morphism are like some. So then you take objects unions of Q polarized Hodge structures. And as morphisms. As morphisms, you're gonna get homomorphisms of you take this Q polarized Hodge structures, you think them as like Q vector spaces. So you take the dual. Sorry. Let me just write, so to save more time that I don't have. I'll just say that we have this category of infinite union of whose objects are like finite unions of Q polarized Hodge structures. They have like appropriate morphisms. They form what is named like a Tannakian category, whatever does it mean. But the main point is that from this category, you can see this as the category of representations of a certain nice group, that is this Mumford-Tate group. The Mumford-Tate group, I wish I could give you more details, but I will not have the time. This Mumford-Tate group, it will act on this H2 star, and in particular, it will act on this even part. And when you look to the fixed part of this action, under this action, so when you look to this fixed part under this action, say this in cohomology, you're gonna get precisely the Hodge cycles. Let's put like this. You're gonna get the Hodge cycles. And the main claim on this part of theory of atoms is that so you get these Hodge cycles, and then you can intersect these Hodge cycles with this even part. Here we have defined quantum multiplication and Euler vector field. The action of the Mumford-Tate group will commute with this. So when you look to this eigenspace for these actions, you can indeed attach to them like because they will commute. So this Mumford-Tate action will passes to this generalized eigenspace for this action, and they will carry like the natural Hodge structures. And to these Hodge structures, this homomorphism class of these Hodge structures controlled by the Mumford-Tate group, you call these atoms. So it's like very, very sorry, I missed the time regarding this. And I said on the statement of theorem C that we were dealing with some kind of categories instead of this Hodge structure, this isomorphism class of Hodge structures. And the main reason for this is that, as I understand, an approach that you do to pass to deal with atoms is that you replace dealing with your smooth projective varieties to some non-commutative space by replacing the smooth projective varieties to the category of perfect complexes on this, and then you then switch with dealing with view cohomologies for smooth projective varieties to Hochschild cohomology. And there is like a nice way to make everything compatible. And then this is just to say that all these things that I'm saying that unfortunately I did not have the time, they could be like at least ideally treated when you pass to perfect complexities and hot-shield homology, but atoms are isomorphism classes of these hot structures. And to obtain our theorems, we construct Z models choosing generators. This is the last thing I want to say. We construct Z models choosing generators. And what shall be these generators? We pick, for instance, these things that we call symbolic generators that are collections of characters, because we are now turning back to the proofs of theorem ABC, and I said that there was the model. So we look to these AI guys here being characters. So you also pick as generators curves with other guys, A1, A2, where this AI also belong to here, but let's put non-zero. Non-zero, and then you also take S3 as P1s, H1, H2. So these are curves with higher genus, so GC greater or equal to 1. And as other symbolic generators, you collect birational types of surfaces and the characters, A1. And you also shall collect then as the atomic, these atoms. But atoms with ZP actions that I through the time I couldn't explain. But so these are like isomorphism classes of Hodge structures compatible with certain ZP actions. Let's say this succinctly. So we collected this kind of like symbolic generators indeed. So you make pairs of this stuff. So you collect the characters, you make these triples, you collect the curves and you make these pairs, you pick P1, you make these pairs. And the surfaces make this. And when you are given with a smooth projective variety, X, the idea is to decouple from it these generators. So you look to the fixed point set. Is there a curve? Then you collect curve with homogeneous. You collect. Then you look to the normal bundle representation characters, and you make the symbolic guy. If there's P1, you do the same. If there are surfaces that's you collect its birational type and the character for the normal bundle action, and you collect their atoms. Now we collect these generators and stud all the possible blow-ups appearing. This will provide the generator like relations on this model. When you make the constraint by this free abelian group generated by these relations, that's aimed to get the data from X, model this relation, you get the birational invariants that I said in the terms of a Z model. Making homomorphism with Z, we guess the formulas on theorems A, B, C. I'm very sorry for being late. Thank you so much.